thank you so much for being willing to talk calculus with me over Zoom, John. Would you take a second to introduce yourself to my students?
Yeah, it's nice to be here. My name is John Brown. I teach high school math in the city of Chicago, Lakeview High School. Um, so I got on here because I don't do calculus every day. So it's nice to work through and cut my skills, keep them sharp.
Alrighty.
Gotta keep them sharp.
And then I'll just probably pester you with questions about things like, why did you do that? And how does that work?
Great. So let me first say why I picked this problem.
Yeah, because that's quite a function.
Is quite a function, and you asked for something where you would have to use different differentiation rules, and I thought to myself, well, I'm really used to seeing these really nasty functions that don't mean anything. And I thought, well, let me try to find a function that's reasonably complicated but actually has a meaning. So actually, I was wondering if you recognize that this function is like
Well,
from
it looks like a different, my thought looking at it was dampened oscillation,
yeah.
but I was unfamiliar with the square root of 1 minus a squared. Like what kind of parameter that might be familiar with. That might
Yeah,
relate to.
exactly. And so that's why I had the thought, okay, let's do a damped oscillator, but I didn't really know, or I couldn't remember, all the details of that from differential equations. So I looked it up on Wikipedia, and I just picked one of the explicit solutions to the damped oscillator, and I probably could pull it up of what the original differential equation is, but it's their students aren't aware, a differential equation is an equation where the unknown is itself a function. And the kind of function you get here is something like a spring going back and forth on the mass, but there's some resistance in it. And so that gives you an equation. And one of the cases looks like this. I kind of picked a particular solution because I thought the general form had kind of too many.
General form has a lot going on.
Yeah, you can have a sign in there, it can have different, you have some choice of like the constants. So I just picked some values of the constants, but I did leave one parameter in there. And I think this is sort of the strength of something like the strength of the dampening, this A. So you can see that. And one thing I thought I would talk about as I was working through it is how important it is to be able to understand the structure of an expression. So we have this standard for mathematical practice called seeing structure in expressions. And when you look at this, you can really get overwhelmed. And sometimes students are like, I don't know what to start, which rule to apply. So you kind of just need to start breaking it down and seeing like, all right, what are the pieces in here? And so the first thing we notice is that there's multiple letters, so to speak. We've got the T, and I noticed, for example, that the T is the input to the function. So that's really what we would call the variable. And there's also a domain restriction over here. T is greater than or equal to 0.
Okay.
And then there's also this other letter, A, and you mentioned the word parameter. Have you talked about that word with them? Like what that
It hasn't come up a lot yet.
So the way I like to say it is that like parameters are things that don't change. You can change them, but once you change them, they're fixed. So they're sort of choices that you make, but once you make them, they are. I tell my students to think of them just as numbers. They're just numbers you don't know. And that's a little bit weird because they're used to thinking of variables as unknown numbers. But we're in the world of a function, right? So this variable is really a different kind of thing. It's the input to the function. The T is the input to the function, whereas the A is a parameter, which describes in the scenario like how strong is that resistance to the oscillation.
Yeah, and we haven't. This is probably on me, but we haven't emphasized a lot that kind of with the idea of with respect to.
Mm-hmm.
So we're talking a lot about rate of change. And in that rate, when we were first doing velocity applications, we talk a lot about time and then kind of
Mm-hmm.
distance over time. But in the general sense uh, of a function, we're thinking about how is the output of the function changing with respect to the variable changing, right? Which we see in
Right.
some of the notation, like the df/dx.
Right. And some of the notation hides that.
Right,
So if I were to write f prime of t, well, I'm not really mentioning, it's sort of implied that I'm taking the derivative with respect to t because t is the only variable there.
right.
But I've got this other letter flying around, and that can be confusing.
Hmm.
So maybe to be explicit, I'll just use the Leibniz notation. And so if we want to take the derivative of this thing with respect to t, we've got to understand the parts. So we know that we have this a, and it is going to be just a fixed number. If you really um, feel like it, you can just substitute in a number like 0.5 for yourself while you work through it, and then imagine um, what would be the steps I would take if a was just 0.5.
Right.
And then you still carry it out, but you keep the a in there. So let's try it. And here's the structure that I tend to kind of go with is sort of blur your eyes and imagine what's the largest scale structure that's here. Um, if you have I used to say with Shrek, ogre has layers. Is it not like an onion? A function has layers. It has the outer layers and the inner layers, and so we want to kind of see what's the outermost layer. So I would look at this and I'd say, all right, well, I have this factor here. This is an exponential, and maybe I'll highlight it in green. I have this factor. Oh, that's too dark. Uh-oh. How do you do this? All right, I'll underline instead. All right, so that's that one factor, and then I have this other factor, and they're multiplied, right? There's an implicit multiplication here. So I start off by thinking, okay, well, the outermost layer is multiplication, so therefore I need to use the product rule. Um, so the product rule would say, okay, well, let's take the derivative of each one. Each one gets its term. So I'll try to write this out as fully as I can. Oh boy. So the first one gets its derivative taken, and then we just write out the rest of this. And I know I'm going to run out of room.
Yeah, the medium we're working in.
Okay, and then we need to add. Now, one nice thing, I already kind of know, because I've done problems like this a lot, that eventually I'm going to have a factor. I'll be able to factor out this exponential later on. So that'll make it a little shorter. I know that because the derivative of an exponential is also an exponential.
Right.
So we'll get there. All right, so then we have d by dt of this thing. I'm going to write dot dot for a second. All right, so let's deal with the first part. This is the easier part because we just need to think through this.
Just one thing I'm noticing there is that you're making choices about kind of writing down partly because of space, but also because you're thinking about just what are you going to attend to and which steps,
Mm-hmm.
right? So you're just thinking about kind of what's important for right now to know.
Yeah, and that's a really important thing to, procedural fluency is not only about knowing what the steps are that you need to write down, but also ones you don't need to. Like, what are you comfortable with as a problem solver doing in your head or leaving out? And as you mature, you can write down less. But when you're new at it, you should write down more because it's easier to see your mistakes when you write down more. If I was doing this on the board, I wouldn't have written an ellipsis there, but I think it is a useful kind of metacognition move to sort of say what do I care about at the moment. Okay, so let's do this derivative. So now we're going to get into a different rule. So we're getting into the layers, and we see we have to take the derivative of e to the minus at. Now, this is something I see a lot of students don't know what rule to apply. Because they're like, do I take it down and subtract 1? What do I do here?
Right.
And again, going back to the seeing structure in this expression, I don't know, what do you say to your students in terms of like, how do they see that that's a composition?
Well, so when we think about like that misapplying the power rule, which like you're saying happens very frequently,
Mm-hmm.
right? So that's kind of being able to notice that that's the variable raised to a constant power,
Mm-hmm.
right? And by this point, students will have seen some geometric representations about then why is the derivative what it is.
Mm-hmm.
But this is a constant raised to that variable power, so it's a very different kind of function.
Right. And again with the extra letters, when we use a letter like e, which is a constant, it's not even a parameter, right? It's just a fixed constant forever.
Right.
That adds an extra layer. You have to be able to recognize that that is not a variable, that is a constant. And by convention, it has a certain value. So yeah, so this is an exponential function. And so, we think about the inside and the outside. A lot of times we say that inside function, outside function. The outside function is e to the blah, e to the something. And so I need to take the derivative of that outside function using the chain rule. So that I know is itself. So I have e to the blah again times the derivative of the inside. So the blah part doesn't change, right? We just leave that alone. There's a lot of times where students do too much. They try
I
to
like that
take,
way of thinking about it. Yeah.
yeah, they try to take the derivative of everything they can see, like over eager. So you just leave the blah alone, you leave the inside alone, and then you take the derivative of this. And so you take the d by dt of minus at. And again, this is a place where that having that parameter makes it confusing. So if you imagine for a second that a was 0.5 and you just had a simple function 0.5t, well, that wouldn't be so bad, right? We would know that that's just the coefficient. And so the same thing applies here. It's just the coefficient, opposite of a.
Right.
All right, so
Even if at that point, like as you were saying, kind of do too much, if you were thinking product rule, right? When we did that second part where we were multiplying by the derivative of a is not the variable, right? So that derivative would be 0. Um, it would kind of would lose that second term.
You mean if I were to
Just even if we were thinking of it minus at as like the product of two things we had to take the derivative of.
Oh, yes.
Yeah.
Yeah, exactly. If you tried to apply the product rule to at, yeah, you would get and that's hard because you're taking the derivative of a constant with respect to t.
Right.
I mean, this is if you think I'm as an aside, this is actually how you have to think when you get into multivariable calculus and doing partial derivatives, right?
Mm-hmm.
So in a way, I'm sort of secretly doing a partial derivative, but we'll leave that aside. All right, so now I got to do this part. So let's do notice what I said earlier is now happening. This minus e to the minus at is going to occur in both terms, which will help me kind of compactify it a little bit. So I have the minus at, e to the minus at, and now I have to take the derivative of this green part. All right. Now, here's another point where I could try to do too much.
Definitely, yeah.
Because this thing here, this square root of 1 minus a squared, You might think, oh, I'm going to have to be doing more chain rules with that thing, but it's not. That's a number. This whole thing is a number. I'm treating it like a fixed value for the purposes of taking the derivative with respect to t. So what I can do is I just, again, imagine I was taking just the derivative of 2 cosine 7t. Well, that's not so bad. I could do that, right? Take the derivative of the outside, minus sine. Take the derivative of the inside, 7. Life is good. But somehow when I put this square root business, it's like,
Yeah, it even looks even more like a variable kind of being set up.
yes. Yeah. And in fact, when I read it, and this is the thing, is when I read it on Wikipedia, I had to look carefully to make sure that the t was not underneath the square root.
Mm-hmm.
And then I had to think about whether it would be, and I realized that it shouldn't be. And okay, so the 2 we know comes in front because it's a constant. It's a multiplicative constant. It comes up front. And then I have the cosine becomes minus sine. Again, of blah. I'm going to not write the blah again. So that's the whole square root of 1 minus a squared times t. And then I have to,
I was
yep,
just gonna say I like that kind of the blah, just even as kind of a encouragement not to do too much.
yeah, you can't do it if you can't see it.
Yeah.
Yeah. Okay, but now I do need to take the derivative of the inside. And again, it's kind of like what I was saying over here. It's complicated, but it's really just a number times t. And so the derivative is just
The number.
the number itself. All right, and now I've actually, there's no more d by dt's anywhere. So I've cranked the handle and I've got, this is the derivative. Now I could probably clean this up. For example, I could factor the dampening part of the exponential here out. And actually there's a 2 in both terms, for example.
Mm-hmm.
And so what I'm left with is something like, in fact, that there's a minus in both. So, okay, so maybe I'm getting a little ambitious, but let's try this. A cosine, what I've been calling blah, plus, I've already taken care of the 2, the minus, and the e to the minus at, and then I have sine of the blah times, and that's just a number minus. So you have some aesthetic choices in exactly how you write it, but that's a derivative that we can say.
Yeah. All right. So so after something like this, like as you acknowledge, is really pretty complex. Do you do anything to check or to kind of see if it feels right, or
Yeah,
how do
good
you sort of
question. Yeah.
verify?
So one thing I was thinking about, let me show you the graph. So I made a graph of this on Desmos, and I made a slider so you can see what the behavior is like for different values of the parameter. So again, intuitively, think of this A as the strength of the dampening.
Mm-hmm.
So if it's 0, we have just a harmonic oscillator, simple harmonic motion. And if it's 1, I think it is just a decay. Yeah,
There's
in
no
fact,
bounds.
look, 1 minus, if A is 1, then this is 0. And so you just have cosine of 0, which is 1.
So we could just get the exponential.
Yeah. In fact, that's actually another math practice, which is being able to imagine what things are like without calculating them out, right?
Mm-hmm.
And that's part of seeing structure and expressions, be able to see, well, okay, well, what if A is 0? What if A is 1? And so in some sense, A kind of tells you which of these two factors is kind of dominant, more important in a certain sense. Like when A is 1, then decay is the only thing that matters, and when A is 0, then the oscillation is the only thing that matters.
I suppose that's when I don't, now that graphing technology is so good, I usually check this way. But I
Yeah.
think back in the before times, if there was a parameter like this, I'd look at the derivative in the original function like for a equals 0, a equals 1, and see if those answers made sense.
Yeah, because it would simplify quite a bit, and you would be able to
Right.
check that you didn't miss a constant or something.
Hmm.
Um, but yeah, I mean, so certainly we can graph the numerical derivative, and then we could type in that nasty thing if I could.
But
Oh well,
here's
but
here's
we do
here's
have.
what
Yeah, here we go. This is
yeah,
nice.
yeah. So here's what Desmos said the derivative was, and then here's this function that you found.
I'd say that's pretty good confirmation.
Yeah, that's good confirmation.
And
And
which is not a way that, yeah, that's not a way that I would have ever checked a derivative um, when I learned calculus. Even though we had graphing technology, we didn't have the ability to graph a derivative
right,
on the TID, whatever
right.
that
And
I.
we actually, before we learned the rules, we were using tech for derivatives. So
Mhm.
you could check against GeoGebra or Wolfram Alpha, where they show you the form of the function as well.
Yeah, one thing that I was kind of was interesting as I was playing around with this graph was that when you graph a harmonic oscillator. In fact, can you put A to 0 for a second?
Hmm.
So that should be the case of a harmonic oscillator. They're sort of in phase, or sorry, they're out of phase, but they're the same function, uh, same form, and the sort of minima of the red, or sorry, the maxima of the green are also zeros of the red, which is not necessarily true because it's the derivative. That's just because it's a solution to the second order equation.
Right. So the whatever's oscillating is moving the fastest right at where it's at that kind of balance point,
Mm-hmm.
and then slows down and speeds back up again as it's going up.
Right. And
Yeah.
that's because if you graph the second derivative, you're going to get back um, a multiple of the original function. Or actually, I guess the exact same function. Um,
In this case, but that probably wouldn't be the case if there's some dampening, right?
right. And so that's what I was sort of saying is that, of course, whenever the original function is at an extreme, you get the derivative being 0, but you don't have the other way around anymore.
Right.
The maxima of the derivative do not line up with the zeros of the original function anymore. They're sort of lagging behind in a way, um, which is interesting. And I don't know enough physics very well enough to know what that's called, but I think they do describe that in terms of the fact that the phase of the acceleration is not it's not the same as the phase of the position, I suppose.
Yeah.
Yeah.
All right. Well,
So that's the problem.
thank you so much. That was what looks like an insanely complicated function to take the derivative of. But I love your connection to thinking about the structure, and then just I think about it almost like persistence. Like you're just kind of taking care of what you need to at each step, and stepping your way through. You even said turn the crank at one point.
Right, and that's what it feels like when you do derivatives. I think I mentioned on Twitter that like in a lot of math, you have a lot of choices in how you do things. But for derivatives, in a way, you don't have a lot of choices. Like the rules kind of come from the structure of the function, um, and they always work, which is nice. Whereas when you do integral calculus, you can bash your head against the wall again to find an antiderivative, and it may not work. Uh,
Right. Not
and
everything we can write down has a nice antiderivative.
exactly. So I think we'll leave it there.
Yeah. Well, thank you so much, John, and
Yeah, it's great to meet
good
you.
luck with the end of the school year. And
Thanks.
for a teacher this year to take time out to do something like this, I just really appreciate it.
Yeah. All right. See you around.
All right. Cheers.